So today's lecture is following up on our discussion of filtering, specifically using software to do the filtering, or what's often called the field of digital filtering. So you'll recall that one of the ways we can filter a noisy signal is through the RC circuit. It's the simplest filter available, simply resistor and a capacitor in this configuration. The voltage comes in on the resistor. The voltage coming out is a smoothed version of the incoming signal. It's called a low pass filter because it passes the low frequency component of our signal. And that's usually where the information is. Often a signal is noisy because it's the high frequency noise that contaminates it. That's not always the case, but for the vast majority of, say, mechanical engineering applications, we'll see something that a low pass filter can be used to clean up. So, and you know, this high frequency noise might be coming from the AC current in the building, right, or a bad ground, or sometimes it's radio frequency signals that the wires in your conductors are picking up. You know, maybe a local radio station or something like that. It happens fairly often, but particularly when we're sampling these signals in an Arduino, this can be very problematic. So what we want to do is kind of lay out just a little bit of theory about this, and then show about how we could construct a program in our Arduino or any kind of MPU, our microcontrolling unit, and to filter that out. So keep in mind here that these signals, in this case E in and E out, are continuous in time. That means they're defined regardless of when we look at them, right? There's an infinite number of values they take on over a course of, you know, whatever period of time we're looking at it. But when you're using a computer in a mechatronic application, you're really taking these individual snapshots at certain instants in time. So, and we're going to assume these are evenly spaced in time, and that spacing will be H. We'll use the letter H to mean the time interval, and we call that the sampling time. So we only have, say, these T0, T0 plus H, T0 plus 2H, and so on. So we basically just have a collection of numbers that represent this continuous time signal in the computer memory. We call these snapshots samples, and again, the H is called the sampling time, and 1 over H is the sampling frequency. So we represent the continuous time signals, we saw them as E sub t, and we represent these samples as, you know, they're at these specific periods of time at kh, where k is 0, 1, 2, 3. But for simplicity, for most of these, we leave off the h part of it because it's the same for all samples, and we just call that E sub k to represent a sampled signal, where k is an integer. And so what we want to do is find an expression for E out, the filtered signal, at k, as a function of E in, the sampled signal at k. That's where we're headed with this. Okay, so to do that, we're going to actually go back to our RC circuit and the differential equation that describes it. Just an RC circuit. The input signal comes on the resistor, the capacitor goes to ground, and the output is the voltage on the capacitor. And the differential equation that describes this, and we can derive this fairly easily, but I won't do it now, is that RC times the derivative of that output voltage plus the output voltage itself is equal to E in. So this is a very simple first order linear ordinary differential equation. We know the solution to this will be exponentials, but that's not what we're interested in right now. What we're interested in is what happens if E in and E out are sampled in time, and what can we do with this equation. And one of the things we can do is we can approximate the derivative using a very simple difference method. In fact, it's the intuitive one we'd expect, that if the signal takes on a certain value at k minus 1 and another value at k, we can find the slope of that line that connects them through a very simple equation, which is k, E at k minus E at k minus 1 divided by the time it took to get there, right? So that's the average slope between those periods of time. So it's not a bad way to look at it. And then we can use that to substitute that back into a differential equation and now come up with a sampled version of that first order differential equation. This is called the backwards difference approximation. There's a few other ones available, but this is the simplest one. So looking back at our differential equation and substituting that back in, we can get to this equation now. Instead of E out and E in as just a continuous function of time, we now have it in terms of the sampled signals. So we have E out at k minus E out at k minus 1 divided by h plus E out at k equals E in at k. So pretty straightforward. And now it's just algebra. What we want to do is we want to find just the expression for E out at k, right? And so we just gather around those terms, do a little math, do a little algebra, and end up with this expression where we have a coefficient that's RC over RC plus h times E out at k minus 1. So that's the last filtered output, plus h over RC plus h times E in at k, so the current input. So we have the sample, E in at this point in time, the last filtered output, the k minus 1, and we add them with these two coefficients. Note that those coefficients, when you sum them together, equals 1, right? So they have the common denominator, so when you add them up, you get RC plus h over RC plus h, so that's unity. That's important to know because that tells us they're not independent, right? So I'm going to let this single parameter a represent the RC over RC plus h, and now our numerical recipe for this filter is simply a times the last filtered output plus 1 minus a times the current sample. And so we see as a is this sort of variable that lets us decide how much we want to weight this new information of the current signal versus the old information of the sample. It's sort of like the momentum of it. So it's very easily implemented. The only thing you have to do is add an additional variable that carries through to the next loop of your execution, so that E output at k minus 1 is defined for us. And of course, as we talked about issues of scope in our programming language, programming environment, that last filtered output has to be declared in the global block, right? The block above the setup. So let's look at what this looks like. So if the tau of our RC circuit, the time constant of our RC circuit, is about 1/3, that means if you get a step change in your input voltage, the output will catch up to it within 5%, within 1 second, and within 3 time constants. So the time constant is 1/3, and let's say the h we're sampling 100 times per second, so h is 0.01 seconds. Then we can easily solve for a, for the coefficient of our filter, by doing this math, and we get 0.3 over 0.34. I made a little mistake there, corrected it. It's 1/3 plus 0.01, which is what h is. There we go. And just do the division, and you get about 0.76, which means that 1 minus a, the other coefficient, will be 0.24, and you've got this very simple equation. So a couple things to keep in mind is that you still need to design this. You still need to understand where it's coming from. You need to know what your time constant is, and you need to know what your sampling period is, and that's really important because it's part of this expression. So usually a good use of the delay function is a great way to do that. So these most of the computations we do in the Arduino are very fast. They're in the microsecond range. So if you delay it for 100 milliseconds or 10 milliseconds or something like that, that's going to dominate that timing. So you won't really see a big difference there. So also the other thing to be concerned about is the aliasing issue, right? And we'll talk about that, or we have talked about that in another environment, but that's always important. So that's it in a nutshell. Thank you.